Hi, so in today's video, we're going to look at the domain of composite functions. So we're going to look at how we can determine the domain of two functions composed, the composite of two functions. So we've got an example here. So let f of x equal 2 to the power of negative x plus 1, with a domain here of x being greater than or equal to 1. So remember, this is our domain, and this is our domain for x. And this is our domain here for g. So x is between pi and 2 pi. Now, if you've not seen radians before, I'm using radians here instead of angles. So obviously, you know a sine graph from GCSE. So a sine graph or a sine wave. Sorry, I've made a mistake here. This should be f here, a domain for f. So obviously, yeah, you would have seen a sine wave in GCSE. So sine kind of has this graph, and you've got 180 degrees there and 2 pi there. Sorry, 360 there in degrees. Now, in A level maths, you use radians instead. You tend to use radians instead. You have questions where you use degrees in the trigonometry. When you solve trigonometric equations, you may use degrees, but in general, with these kind of functions, we generally use radians. So just remember that pi is this. So pi radians is the same as 180 degrees, and 360 degrees is the same as 2 pi radians. So I'm using radians here. We'll come on to that in future videos. So yeah, so what is the domain of the f composite g? So f of g. So remember, this means it's just means f of g of x, and this one here means g of f of x. So g composite f. So how do we determine the domains of these functions? So let's start with the first one. I've got a lot of information here, so let's just go through this. So we want to find the domain of f of g of x. So in order for this function to be defined, we obviously need g of x to be defined. So, I mean, in order for this to exist, obviously g of x needs to exist itself. If that doesn't exist, then this whole thing doesn't exist. Okay, so that's fine. So in other words, we need, yeah, g of x to exist, and we need, well, in order for g of x to exist, we need x to be between pi and 2 pi. So we go back here. G of x only exists if x is between pi and 2 pi, because we chose that. We arbitrarily, the question told you this function only exists in this domain here. So in order for this function to exist, we need x to be between pi and 2 pi. Okay, so that's what we need. Now, also, we need f of x to be defined as well, because again, if this doesn't exist, then the whole thing doesn't exist. And we need, so for f of x to be defined, we need x to be bigger than 0. Now, that means for f of g of x to be defined, we need g of x to be bigger than 0. So whatever number we plug into f, we're told here that, yeah, whatever number we plug into f, it must be bigger than 0. So if we plug g of x into f, well, it better be true that g of x is bigger than 0. So we need g of x to be bigger than or equal to 0. So the question is, when exact, so for what x values is g of x bigger than or equal to 0? So g of x equals sine x, and this is only true, we're told, when x is between pi and 2 pi. Now, we know from a sine graph, if you think about our sine graph again, looks something like this. We've got 0 degrees there, 180 degrees there, but just if you've not seen radians, it's pi radians. It's just the same as pi radians. And this is 2 pi radians here, which is the same as 360 degrees. Now, when x on your x-axis is between pi and 2 pi, what we can see here, I mean, this is 1 up here, this is -1 down here using our sine graph. This is y equals sine x. We can see that sine x is negative. So in our domain, this is our domain for g. So domain for g, we can see that sine x is less than or equal to 0 for all of these x values in this domain of values. So that's basically just what I'm saying here. I'm saying that it's negative for all x numbers in the domain of g, and our domain was this domain here. That's all I'm saying here. But we can see from our graph that when you substitute pi into g, you get 0. We can see from the graph. And when you substitute 2 pi into g, this function, you get 0 as well. So 0 is bigger than or equal to 0. I mean, pick the number 10. 10 is bigger than or equal to 0, isn't it? Because 10 is equal to 0. So 0 is bigger than or equal to 0 because 0 is equal to 0. So basically what we're saying is that if x equals pi or if x equals 2 pi, then f of g of x must exist, because we know that in such case, we've got g of x to be greater than or equal to 0. We need g of x to be greater than or equal to 0 to exist. And we also need x to be in our domain for g between pi and 2 pi. So what values of x give us g of x bigger than or equal to 0 within this domain over here? Well, it's pi and 2 pi. So basically, f of g of x exists when x is either pi or 2 pi. So this would be our domain. So our domain here is pi and 2 pi. Okay, so that's kind of like a, I guess, maybe not a clear example, but hopefully that kind of does make some sense. That we want to ensure that this exists, this g function. So we want to ensure that x is in the domain of g, but we want to ensure that this range of g, this g function, falls into the domain of f, and the x values which give us that will be our domain for this composite function. So this is kind of like the general rule then. So if you have a function f of x and you have a domain x in a set A, where A is a set, obviously that means you've got a range of f of x values. That's your range there. And let g of x have a domain x in another set B. So the range is, again, here with g, the set of g values that you get when x is in your domain. So the domain of f of g, so the domain of f of g, I'll do this in a different color again. It's in blue. So this will be the set of x values in your domain of G. So the set of x values in this set there, such that G of x will be in the set A. So G of x will be in the domain of A. So in English written words, what does this actually mean? So the domain of f of g, the domain of f composite g, is the set of values in G's domain, the set of x values in G's domain, such that g of x fits into f's domain. So if as long as you've got x values which are in G's domain, and also those x values give you g values that fit into f's domain, then therefore you've got the domain of the composite function of f of g. And a similar result with this here. So if you've got the function g of f of x, so g composite f, that domain will be the set of x values in A. So the set of values in f's domain, the set of values that exist in f's domain here, such that this f of x belongs in the domain of g. So as long as you've got x values which are in f's domain and they belong in G's domain, or they give rise to f values that go into G's domain, then you get the domain for the composite of g of f of x. So again, in written words, the x values in f's domain such that f of x fits into G's domain will be your domain for this g composite f function. Okay, so then if we go to like a diagrammatic example, so let's say you've got a domain for f between 0 and 3, and a domain for g between 1 and 5, and let's say the range of f is from 0 to 5, and the range for g is from 1 to 4. So what is the domain of f of g? So again, f of g of x can only exist if g of x, this g of x, is in f's domain. If g of x is in f's domain, it will exist. So what is f's domain? Well, f's domain we can see from the diagram. Yeah, the domain of f, this is a mistake here. This should be 3 here. My bad. Sorry, let me change this to a 3. Shouldn't be 4 there. F's domain is 0 to 3. Let me change that to a 3 too. So yeah, so for f to be defined, we need x to be between 0 and 3, because we see that from the graph. So we need g of x to be between 0 and 3, because we're plugging in g of x into f. We're not plugging in x, we're plugging g of x in. So we need g of x to be between 0 and 3. Okay, so the range of g we can see is 1 to 4, this green one, sorry, this blue one here. So the range of g is 1 to 4. So what will the domain of f of g be? So the domain will be the set of x values in G's domain such that g of x is between 1 and this should be 3. I'm going to change this to a 3. This is a mistake here. And this is also incorrect here. This is not a subset of this one here. So the key thing to look at is we're going to look at this set of values and this set of values. So where do these g of x values intersect? What is the intersection of this of these two lines. So you've got 0, 1, 2, 3, 4. So the top, this top one here, this 0 to 3 is something like this. That's 0 to 3. And 1 to 4 is something like this. Where do they intersect? Where do they overlap, these sets? These sets overlap here from 1 to 3, not including 3. So actually our domain, or our domain will be will arise from the set of x values such that g of x is trapped between 1 and 3. So bigger than or equal to 1 or less than 3. That would be our domain there, because we need g of x to be bigger than or equal to 0 and less than 3. But the range of g goes between 1 and 4. So therefore the set of g values in which f of g will be existing for will be 1 up to 3, because again we need g of x to exist. So we need x values such that well, we've got a range of g values between 1 and 4, but we need g to be between 0 and 3 because the domain of f is 0 to 3. So where do these regions intersect? They intersect at 1 to 3. Okay, so now if we go to g of f of x, a similar kind of thing. So for g of f of x to exist, f of x must be in the domain of g. It's got to be in g's domain. So the domain for g is 1 to 5. We can see this again up here. The domain to g of g is 1 up to 5. So we need f of x, because we're plugging in f of x into g, to be between 1 and 5 as well. Okay, so the range of f of x is 0 up to 5. We can see that here, f of x, this range, this red range goes from 0 to 5. Now, it's like kind of similar to what we did back here. Where is the intersection between this set here and this set here? So these sets overlap between 1 and 5. So in order for so the range of f of x values again is 0 to 5. We can see that from the diagram there. But we need, in order for this function to exist, we need f of x to be between 1 and 5, because the domain of g is between 1 and 5. So where do these sets overlap? If we think about a number line again, this number line goes from 1 up to 5. That's our number line here. This number line down here goes from 0, including 0, up to 5. So where do they overlap? They overlap between 1 here and 5 there. So this is going to be our domain. So our, well, not our domain, but our set of the set of x values which give us this domain of values. So let me repeat that again. It's the set of x values which give us f of x values between 1 and 5 will be the domain. So again, the domain of g of f is the set of x values in f's domain such that f of x is between 1 and 5, and we can again see that from this analysis here. So yeah, I mean, let's go to an example again to put this into practice. So we know that g of f of x is just going to be the same as, if we just write this here, so g of f of x is going to be the same as g of 2 to the minus x plus 1. Okay, so for this function to exist, we need 2 to the x 2 to the minus x plus 1 to be between so to be in the domain of g. So we need pi to be less than or equal to this 2 to the x plus 1, 2 to the minus x plus 1. Yeah, between pi and 2 pi. So that's what we need, because in order for g to be defined, that's our domain, that's our set of values that we need. Okay, but now where does f exist? So we actually need this f function to exist as well in order for that to be true. So f exists when x is greater than or equal to 0. We can see that up there. So okay, so this is going to exist when x is greater than or equal to 0, and also when 2 to the minus x plus 1 is between pi and 2 pi. Okay, so when is that the case? So when is 2 to the x minus 1 sorry, 2 to the minus x plus 1 between pi and 2 pi? So when is that the case, and when is it greater than 0? Okay, so so what we're going to have to do is just look at the set of x values that we have given here then. So if we take away this, if we look at this first inequality here, I call this number 1, I call this number 2. So with number 1, we can take away 1 from both sides, and then we get pi minus 1 is less than or equal to 2 to the negative x less than or equal to 2 pi minus 1. So just taking 1 from all of the parts of the inequality there. And then, okay, so now then, if we want to find the set of x values, we're going to have to take logarithms. Now, we've not seen logarithms yet in these videos. However, what you would do in such a case is you would take logarithms. Now, if you take logarithms of the base of 2 on both sides, so log base 2 of this number, and then log base 2 of this number, less than or equal to log base 2 of this number. What that does is it gets rid of the power with a base of 2 here. It gets rid of the power of 2 there. Again, we'll come on to this in future videos, so don't worry too much about this for now. Logs are the inverse of exponential functions. So the inverse of exponential functions will remove this. We'll come on to inverse functions as well very soon. So what you'll get is you get log base 2 of pi minus 1 is less than or equal to negative x, which is less than or equal to log base 2. So I forgot the base 2 down there. There should be a little 2 down there. Log base 2 of 2 pi minus 1. Okay, so that means then that x, so that's minus x, but how about x? If we just multiply everything by minus 1, now that means we've got to change the sign of the inequality if we do that. So you get log base 2 of pi minus 1 is greater than or equal to x, which is greater than or equal to, minus sign there as well, minus log base 2 of 2 pi take away 1. Okay, so that's going to be our set of x values. Now then, so where is it the case that x is between those two numbers and also greater than 0? So we need x to be greater than 0 in order for this in here to exist, but we need x to be between these two numbers in order for our g to exist, because we need the f of x to be between pi and 2 pi in order for our g of f of x to exist. So we need x to be bigger than this negative log base 2 pi minus 1. Now I'm just going to go to my calculator and type this into my calculator. So log with a base 2 pi minus 1. So that would give us, so this is going to be a negative, so this number here is a negative 2.4 roughly to 1 decimal place. And then this number over here on the left-hand side here is going to be negative. So just typing this in my calculator. So this is going to be negative 1.0, well, 1.1 essentially to 1 decimal place. So x must be between negative 1.1 and negative 2.4. But x must be bigger than 0. Now, we've got a bit of a contradiction here because there is no intersection between x being bigger than 0 and x being between minus 1.1 and minus 2.4. Again, if we think about like a number line, got 0 in the middle there. So we need x to be bigger than or equal to 0. So we need this. But we need as well the intersection between negative 1.1 and negative 2.4. So we need this as well. They don't overlap. This set here does not overlap with this set of x values there. So actually, there is no domain. So this function does not exist at all. So therefore, there is no domain. So no domain. So actually, the domain would be the empty set. So this kind of like 0 symbol with a line for it is called the empty set. So there is no domain. So therefore, there is no function. This function does not exist with these set of domain values. So that was just another example of how we can calculate the domain of composite functions. And the key thing to note is that for to calculate the domain of f of g of x, this is the set of x values in g's domain such that g of x is in f's domain. And the domain for g of f of x is the set of x values in f's domain such that f of x is actually in G's domain. So we just want to look at the intersection between the set of x values in F's domain and the set of x values which give us the range of f, but it falling within G's domain, and that would be our domain for the composite functions.